Hello children, in today's class we are going to discuss the entire chapter of sound. That is, we are going to make a one short video for this one entire sound chapter, children. So if you need, in detail discussion, previously already we uploaded the sound chapter unit wise. So links will be given in the description. Just kindly go through those videos so as to have a in detail discussion about sound. So in today's class, as I told you that one shot, might be in 1 hour 30 minutes, might be I'll try my level best. But children, what is our main intention? We have to learn the entire chapter in a less time, but we should not miss important points. That is our intention, and that is the main aim of this today's class. Okay, fine. So now get ready with a pen and notebook, so that what will happen, you can note down some important points. Clear? Fine. Now without doing any delay, let us start the sound chapter. Children, this chapter is not it's a new one actually to all class 10 students. Already you learned in a 9th class, 8th class in the previous class, right? So what will happen, so without touching basics much, just we'll try to enter into the concepts. Okay, fine. First of all, what is the sound, children? Yes, what is the sound? Think once again. Yes, so sound is a form of energy. When it reaches our ear, what will happen? It makes our eardrum to vibrate, so that what will happen? We feel a sensation of hearing. So sound is a form of energy which produces sensation of hearing in us. Then how this sound is produced, children? Yes, vibrating bodies will produce a sound. All vibrating bodies produce sound. But the question is that, can we hear the sound produced by all vibrating bodies? Then we can say no. Children, again I repeat once again. All vibrating bodies produce sound, but we cannot hear the sound produced by all vibrating bodies. Here one condition is there. The sounds with less than 20 Hz are called infrasonics. The sounds with more than 20,000 Hz are called ultrasonics. So these are not audible to us. We can't hear. We can't hear the sounds with less than 20 Hz frequency. At the same time, we can't hear the sounds with greater than 20 Hz frequency. We only can hear the sound with a range 20 Hz to 20,000 Hz called audible range, audible sound, or else sonic sounds. Is it clear? Fine, children. So here, before going to enter into the topic in depth, children, let us try to understand what is actually wave. Then here you may get one doubt actually. So why we need to learn about wave? Yes, because sound can propagate in the form of wave. So if you can understand some terms related to the wave, then it will become very easy to us to understand, more about the sound. Clear? Fine. First of all, what is a wave, children? So to understand this, just let us take a situation. For example, so there is a bucket of water in front of you. So what happens when you touch the surface of the water with your finger? Then water will get disturbed. Okay, so you can see some ripples are formed. But do you think that the ripples will stay at the point where you are disturbing? No, they will travel in all directions. So what are we doing in a water, children? Yes, we are creating a disturbance. That disturbance is going in all directions. Is it clear? That ripples, in terms of science only, we can call it as a waves. If in a large amplitude, we can say it as a waves actually. So how to define a wave, children? Here, the disturbance created in the medium which can travel in all directions with equal speed. I repeat once again, what is a wave, children? The disturbance created in the medium which can travel in all directions with equal speed is called what actually? Wave. But the one interesting thing about the wave is that, children, during the propagation of wave, molecules in the medium, they do not move. Rather, they can vibrate from their mean positions. Children, this is very, very, very important. So what do we expect? We expect that molecules will be moving. No, molecules in the medium, they do not move. As a wave is propagating, what will happen? Those molecules will be vibrating, either what we can say perpendicular to the propagation of direction of wave or parallel to the direction of propagation of wave. It depends on the nature of the wave. Clear? Fine, children. As I told you that either particles of the medium or molecules of the medium are vibrating from their mean positions. So one particle at a certain time may get displaced maximum actually. So that only we can express in terms of amplitude. So children, what is the amplitude here? The maximum displacement of the particle from its mean position on either of sides is called amplitude. I repeat once again, what is amplitude, children? The maximum displacement of the particle from its mean position on either of sides is called amplitude. So amplitude usually we can express either meters or in centimeters. Fine. Now what is a wavelength, children? It's very important. Wavelength. So as just we learnt of what actual wave means. As time passes, what will happen? The wave is propagating, right? Yes. So the distance traveled by the wave in a given time period, one time period, means in a one time period, what is the distance traveled by the wave can be expressed in terms of wavelength. In a simply, children, the distance traveled by the wave in a one time period is called wavelength. Even this wavelength can be defined in terms of longitudinal wave, in terms of what is the transverse waves. If it is in the case of longitudinal wave, children, what we can say, the distance between the two consecutive either compressions or rarefactions is called wavelength. Whereas in terms of transverse wave, children, the distance between the two consecutive crests or troughs is called wavelength. So this wavelength we will represent with the lambda. It also can be expressed in terms of meters or centimeters. Then come to the time period, children. What is the time period? So children, as a wave is propagating, what will happen? So the wave has to be completed. Means, for example, if it is in terms of what we can say, means the wave has to be formed in order to propagate, right? So further some time should be taken. The time taken for one complete wave, yes sir, the time taken for a complete wave is called time period. If it is in terms of longitudinal wave, so we can say one compression plus one rarefaction. Okay, to form one compression, one rarefaction, what is the time taken? Whereas in terms of transverse waves, the time taken for one crest plus trough is called what actually? Time period. So what is the time period, children? The time taken to form one complete wave is called time period. So usually it is expressed in terms of seconds. Now come to the frequency. Children. So what is the frequency? The number of waves produced in a 1 second. The number of waves produced in a 1 second is called frequency. So how frequency and time period related, children? Yes, frequency is nothing but the reciprocal of time period, which means what? If more is the time period, less is the frequency. Less is the time period, more is the frequency. What are the units of frequency, children? Yes, frequency is measured in terms of hertz. Here one important factor is that frequency and time period both depends on the source. Both depends on the nature of the source. Whereas wavelength, and here one more thing is there, wave velocity. What is the wave velocity, children? The distance traveled by the wave in a 1 second. Don't get confused. Wavelength is what? The distance traveled by the wave in a one time period. Here the distance traveled by the wave in a one velocity. What we can say? 1 second. The distance traveled by the wave in a 1 second is called wave velocity. Clear? So here wavelength and wave velocity depends on the properties of the medium. Very important, children. Properties of the medium. Clear? Fine. And how wave velocity and frequency in the lambda relate, children? Yes. So wave velocity is equal to frequency into lambda. So in exam we may expect a questions based on this. Simple numerical. So wave velocity is equal to frequency into lambda. Clear? Fine. So these are the terms related to the what we can say, children, is a wave. Fine. Okay, now we discuss the types of waves, children. So here mostly we will be talking about actually what we can say mechanical waves and electromagnetic waves. Of course, in that also our concentration is only on mechanical waves. So these mechanical waves are also called as elastic waves, children. So then what are mechanical waves here? The waves which require a medium for the propagation are called mechanical waves. Obviously electromagnetic waves, they do not require a medium for their propagation. Okay, fine. So again, children, here as I told you that as a wave is propagating through the medium, the particles of the medium vibrate. but in all cases they may not vibrate in a similar manner. So here, based on how the particles are vibrating, based on that, again here we have types, right? That is longitudinal waves. Children, under mechanical waves only we are learning longitudinal waves. So here, what are longitudinal waves? Children, the waves in which particles of the medium vibrate parallel to the direction of propagation of wave are called longitudinal waves. I mean what? When the wave is propagating, children, the particles will be vibrating parallel to the direction of propagation of wave. Okay, fine. So here, the one very important thing is that here, longitudinal waves can propagate through all types of medium. So they can travel through the solids, they can travel through the liquids, they will travel through the even gases also. Clear? Fine, children. So here, example. So example for longitudinal waves means what? Sound waves in air. Sound in air can propagate in the form of longitudinal wave. But how to find the speed of the longitudinal wave in air is nothing but what actually sound only, right? So here it is given by V is equal to square root of gamma P by rho. So children, here is gamma is what actually? It is a ratio of what we can specific heat capacities at a constant pressure and a constant volume. Its value is 1.4. P is a pressure. Okay, now rho is what actually? It's a density. So children, examination point of view, they may ask us what we can sort of write on which factors does the speed of sound depends. Children, here the speed of sound depends on temperature, right? It depends on temperature. So here what will happen here? For every 1 degree Celsius rise in temperature, the speed of the sound is increased by 0.61 meter per second. Means as you are increasing the temperature, velocity of the sound in air increases. How, children? For every 1 degree Celsius rise in temperature, the speed of the sound is increased by 0.61 meter per second. Okay, fine. And the second one, here, humidity, children, here. So the speed of the sound increases with the humidity. So as the humidity increases, what will happen? Speed of the sound also increases. And the third one, children, the speed of the sound decreases with the density. I mean what? If the density of air increases, then what will happen? Speed of the sound decreases. Here the very important thing is that then what happens to the pressure? The important factor is that the speed of the sound does not depend on pressure, because as pressure increases, density also increases simultaneously. I mean what? P by rho ratio remains constant. So here speed of the sound does not depend on the pressure, does not depend on the amplitude, does not depend on the frequency and wavelength. So in exam they may ask a question. So if the speed of the infrasonic wave in air is 330 meter per second, then find the speed of the ultrasonic wave in air only. 330 meter per second only. Why? See, infrasonics and ultrasonic, they might be differ in a frequency, but speed of the sound does not depend on the frequency. Is it clear? Fine. So this is all about the longitudinal wave. And the second type of wave is what actually here is a here one more thing, children. So during the propagation of longitudinal wave, compressions and rarefactions are formed. Compressions and rarefactions are formed. Means one compression plus one rarefaction only, we can call it as a one lambda. Clear? Fine. Now come to this transverse waves. Transverse waves. So what are transverse waves, children? So the waves in which the particles of the medium vibrate perpendicular to the direction of propagation of wave are called transverse waves. For example, the waves produced in a stretched string comes in a transverse wave. And one more important thing is that, children, here as we discussed here, longitudinal waves can propagate through all types of mediums, but transverse waves, they can propagate through the solids and only on the surface of the liquids only. Clear? Fine. So then how to find this velocity, because look at here. So the velocity of the transverse wave produced in a stretched string. So here V is equal to square root of tension by m. Here m means it's not a mass, children, mass per unit length. Linear mass density we can call it. Linear mass density. T is what actually? Tension. As the tension in the string increased, obviously the velocity also increased. So here what, this what, children? Here m is what here? Mass per unit length. That is what actually linear mass density. So these are the types of waves and finding their velocities. Clear, children? Fine. And children, what happens when sound can propagate from one medium to another medium? One medium to another. So children, I mean to say refraction, like light, yes, sound also can undergo refraction, no doubt about regarding the refraction of the sound. So, but important thing is that what properties will change when a sound will propagate from one medium to another medium. Children, when a sound propagates from one medium to another medium, very important thing is that here speed will change, velocity will change, wavelength will change, intensity will change, but the important thing is that frequency remains constant. For example, ultrasonic wave is passing from air to water. So as long as it is traveling in air is ultrasonic, the moment when it enter into this water, do you think that it will become infrasonic or other thing? No, it's not like that. So frequency remains constant. Frequency remains constant. Clear? Fine. Now come to the reflection of sound. Oh my God, ink is leaking. One second. Yeah, reflection of sound. Yes, so when I say reflection of sound, you can recall reflection of light. Yes, like light, children, sound also will undergo reflection. So what is the reflection, children, here in terms of light? When a light falls on any surface, like a especially smooth surface, it bounces back. Similarly, when a sound strikes any surfaces, either rough surface or smooth surface, it bounces back. This only we can call as a reflection of sound. Like light, children, sound also will obey all laws of reflection, which means what here? The incident sound, reflected sound, normal round, all will be lying in the same plane at a point of incidence, and angle of incidence is always equal to the angle of reflection. But what is the condition here? Very important thing. What is the condition? For suppose, children, let us say A is the size of the, very important, size of the reflector or obstacle, size of the reflector, and a lambda is the wavelength of the sound, wavelength of the sound. So what is a condition to occur reflection of sound? Children, in exam what is happening, if they will ask to write the condition for a reflection of sound, students are thinking about echo. Children, please try to understand. Echo is a different again. Reflection of sound is different. All reflections may not produce echo. Some conditions will be there for that also. We'll discuss next. So here I am talking about the only reflection of sound. So what is a condition to occur reflection of sound? So here size of the reflector must be very much greater than that of the wavelength of the sound. When this condition is fulfilled, children, then what will happen? Sound will show a phenomena called reflection. Done? Okay. Now come to the echo. So what is an echo, children, here? Yes. So echo is nothing but the reflected sound, but in all cases we can't feel that, we can't hear that. Okay. For suppose, children, here one obstacle is there. Here one person is there. Okay. So the person makes sound, fires a gun, with a whistle he can make a sound, or he can shout also. Okay. So what, let us say this is D is the distance between the source of sound and the obstacle or a reflector. Then what will happen? This sound will just go to the obstacle. Yes. Here what will happen? It touches and it bounces back. So called reflection, right? So it is traveled in this direction. Please try to understand, children. This is called actually here incident sound. This is what actually here reflected sound, children. Very important. This is what actually reflected sound. But can we feel reflected sound in all cases? Means no, it is not that. if this reflected sound will reach the person in a less or greater than or equal to 0.1 second. Means what I mean to say that there must be some time gap between incident sound and a reflected sound. Okay, for example, the person is shouting from here. How many sounds he can hear? Two sounds. Don't get confused. See, because now I am talking, don't you think I am able to hear my own original voice? Yes. But the reflected sound also can be heard if some conditions are fulfilled, right? Yes, I am talking about that only. So, what means I mean to say that here, completely this original sound should be ceased. After that, what is the reflected sound which is heard? Only we can call it the echo. So, what is the echo, children, here? The reflected sound which is heard after original sound has ceased out. Okay, means from a distant object, of course, is called actually echo. What are the conditions here? The first condition, children, here, time should be greater than or equal to 0.1 second. I am talking. Means, so here the reflected sound should reach the ear of the, what we can say, the person who is observer, let us say that, should be 0.1, least to the 0.1 second, might be greater than 1 second also. Is it clear? Fine. And the second condition is that when you will talk about air, children, very, very important. When you talk about the air, in air, very important, in air, the distance between, the minimum distance between abstract and the source should be 17 meters. 17 meters. Then you may get, sir, how we know that 17 meters? Look at here. Children, here we know that velocity is equal to speed is equal to distance by time. Here distance means don't take d, because in a time t it is traveling d distance forward, d distance backward. D plus d, how much it is? 2d. 2d by t. Okay, now. So in air the speed of the sound is approximately, we can take it as a 330 meter per second. Now use this formula as v is equal to d by t, t is equal to, so we want, sorry, d, right? Just wait. So here d is equal to vt by 2. So that is 330 into 0.1 by 2. So if you can take, you'll get a 16.5 meters. 16. So that's what approximately I wrote a 17. In exam if you write, because rounding off, right? If you write 17 meters, it is accepted. But children, when water, again it's different, very, very important. In a water, the speed of the sound is approximately 1450 meter per second. Then what should be the minimum distance, children, here? D is equal to 1450 into 0.1 by 2. So this will be 2 7s are 2 2s are 1.5. So 72.5 meters. This is the minimum distance. There must be in a water, children. What is the minimum distance should be there between the reflector and the source of sound to hear the echo, children, here? 72.5 meters. This is the second condition. First condition about the time. Second condition about the distance. And here, what is the third one? Yes, obviously, the size of the reflector should be very much greater than that of the wave or wavelength of the sound. And the fourth one is that, children, here. So the sound should have enough intensity such that after striking the reflector, it should come back and should be heard. For suppose if you are standing in air in front of a wall is at a 50 meter distance. If I say hello like this slowly, can I hear the echo? Not at all. So whatever the sound which is produced, that should have enough intensity so as to get reflected back properly. Clear? Fine, children. So these are the conditions for echo. Just copy it. Now we discuss the applications of echo. Dolphins. So children, these are the some important applications of echo. So here sonar, children. What is sonar here? Sound navigation and ranging. So usually it is used to find the depth of the ocean. Some similar cases. Okay, fine. And here ultrasonography, children. So we know that in order to, whenever there is a problem in our body, to check whether the internal organs are working properly or not, yes, we can use this method called ultrasonography. Next, echocardiography, so which is used to see the function of the heart. Okay, fine. Now come to the radar, children. Radio detection ranging. Children, sonar means what here? Sound navigation and ranging. Radar means what? Radio detection and ranging. So what is the main difference between these two children here? In a sonar, we use ultrasound, right? We use, in fact, of course, here and here, in all these cases, here ultrasound or ultrasonics. But whereas in a radar children here, electromagnetic waves are used. And here one important point, why only we are using ultrasonics, why not infrasonics, why not audible range children? Because of some ultrasonics have some special properties. So in exam also they are very important. What are the special properties of the ultrasonics, you know, so that they are used much in many fields children? The first one is that they are having energy, what we call high frequency, which means high energy. They are very high energetic. Second one, what? High directivity. Means they can travel through a medium without getting absorbed much. And third one, they are confined into narrow beam. So because of these three main properties only, they become very famous, we can say that, and we are using them like anything. Clear? So this is about the echo and applications of echo. We will see the natural vibrations or free vibrations. The children, examination point of view, this point is a very important. Now let us see what are natural vibrations. Children, the periodic vibrations of an object in the absence of external force acting on it is called or are called free vibrations, which means what here? Again I repeat, the vibrations, what kind of vibrations? Periodic vibrations of an object in the absence of external force acting on it are called natural vibrations or free vibrations. The time taken for one complete vibration is called natural time period, and its frequency is called natural frequency. So children, the very important, the natural frequency or the natural time period depends on shape and size of an object which is executing natural or free vibrations. Is it clear? Fine. So examination point of view, examples are very important. So what are the examples children? Yes. So again I am telling you, in the absence, the keyword is here what actually? In the absence of external force, that is the external medium. I mean what? Should happen only in vacuum. Is it clear? Fine. So example, the oscillations of simple pendulum in a vacuum. Okay, the vibrations of tuning fork in a vacuum only. Examples for natural or free vibrations. Is it clear? Fine children. And then one important point, as there is no external medium, which means what? There is no external resistive force. As there is no external resistive force children, then obviously what will happen, you know, the body which is executing natural vibrations does not lose any energy. As it is not losing any energy children, its amplitude remains constant. This is very important. So the amplitude of a body which is executing natural vibrations always remains constant. Why? Because there is no external resistive force. Clear? Fine. Now examination point of view, the displacement time graph. Yes, here you can see on the screen children. Yes, so here is displacement time graph of a body which is executing natural or free vibrations. So there if you can see here, amplitude as time is passing, but amplitude remains constant. Amplitude is not at all decreasing. Is it clear? So this graph is examination part of it, it's very important. Okay, now fine. Now we'll see a few more examples for a natural or a free, what we can say examples for a frequency of a natural or a free vibrations. So here first one children. So let us take the simple pendulum. So this we all are very familiar. Simple pendulum. Now look at here. So here is rigid support. Okay na? And here is a bob suspended by means of a string. So it is its center of gravity, and here is its length. Okay. Now if it is made to oscillate in a vacuum, such a vibrations only we can call it as a natural or free vibrations. And its frequency children here, the frequency of the simple pendulum executing what we can say natural vibrations, F is equal to, this is 1 by 2 pi into square root of G by L. So if you here, if you can see 2 pi G remains constant, then here what children here, F is inversely proportional to the square root of L, which means what here, as length increases, the frequency decreases. This is very important. So in exam they might ask a question based on a frequency and a length. So frequency is inversely proportional to its length. As length increases, frequency decreases. As the length decreases, frequency increases. Okay. So here only children, if for suppose if G is equal to 9.8 meter per second square and L is equal to 1 meter, if you can substitute, then F is equal to, you will get 0.5 hertz. And if you will calculate this time period, so we know the time period is equal to T by 1 by F. So we will get T is equal to 2 seconds. So such a pendulum only we can call it the seconds pendulum. Okay, children, can we hear the sound produced by this type of pendulum? No. Why? The frequency of this pendulum is 0.5 hertz. So it comes under infrasonics. Clear? Fine, children. Now let us say second example. So here let us take a load suspended by means of a spring. I mean, we can say simply spring mass system. So for suppose children, here is a rigid support, here is spring, so here is mass M is suspended, so here K is what actually? Spring constant. Then, so children, what will happen if this mass is little bit pulled and it is left? Then what will happen? It will be executing, but children, in a vacuum only. Okay, so frequency is equal to 1 by 2 pi into square root of K by M. This is very important. I means what here, children? Can we change the frequency? Yes, we can change. For a given spring, K remains constant. But if you are changing the mass, so means for a same spring, if you are using a different masses, the frequency will be different. Okay, and the second case, by keeping the mass remains constant, if you are changing the spring, K value will be changing. Hence, frequency also will be changing. Clear? Fine, children. And here, third one, tuning fork. Yes, when a tuning fork is hit, okay, now with a rubber hammer, then what will happen, children? Yes, it will be vibrating with its own natural frequency. And what is the special to the tuning fork? Yes, so tuning fork is a device which produces sound with a constant frequency, so called full note. Very important. Okay, so which produces sound with a constant frequency. Okay, now fine, children. Now here one more very important thing is that, so children, we know that string in a musical instrument, for example violin, okay na, and veena, such a what we can say, musical instruments is there. So what will happen when you can just disturb that string? Then what will happen? They will be vibrating with its own natural frequency. But how to calculate that frequency? So here, children, so the frequency of that string which is executing the natural vibrations is equal to 1 by 2L into square root of T by pi r square d. So which means what here? Frequency of a vibration so produced depends on its length of the string, tension of the string, thickness, r is what? Radius, thickness of the string, even density of the string. In exam they may ask you a question, how can you increase the frequency or how can you decrease the frequency? So let us come here, children. So here if you can see here, F is inversely proportional to the length, which means what here? As length increases, frequency is decreased. Okay, now as length decreases, frequency is increased. And here frequency is proportional to the square root of tension. So frequency increases with the tension. And here frequency is inversely proportional to the square root of or r square, which means what? It's inversely proportional, simply it is a r. So by decreasing the thickness of a given wire, we can increase the frequency so produced. And here the frequency is also inversely proportional to the density of the string which is used. So which means what here? Look at here. So by increasing the tension or length, radius, density, by decreasing these three things, we can increase the frequency of the natural vibration so produced. Okay na? So these are the few examples. Clear? Just you copy it. Fine. Children, even in the case of flute, okay na? So in the case of flute also, what will happen by closing and opening the holes? What will happen? We can produce the sound with the different notes. But by closing and opening, actually what are we trying to do, children? Yes, there we are trying to change the length of air column. There, what is the vibrating body, children? Air column, right? So then how does the frequency produced depends on the length of the air column? Inversely proportional. As the length increases, the frequency of the note produced decreases. Okay, now fine. And this last one, children, it's examination point, it's very important. And I noticed that many students, they are getting confused here. That's what let us spend a bit more time to understand this case. So this is what actually the case, children. So here is one string is stretched between two rigid supports. Let us say the string with the length L. So before going to understand this, children, actually this concept is related to the stationary waves. Of course, in a 10th class standard we don't discuss much. So I'll try to tell you in a very what we can say in a shortcut. I'll tell you stationary wave. How the stationary wave is formed? If one wave is going like this, for suppose, okay, it's called actually incident wave. If it hits any obstacle, it gets reflected back, and these two waves will get superimposed, of course with the same frequency. Some conditions will be there. So as a result, what will happen here? Loops are formed. As a result, loops are formed. Here, children, the very important thing is that here, if you can see here, so here these are the points with the zero displacements called nodes. These are the points with the maximum displacements are called antinodes. So here the very important thing is that, children, in the case of a transverse wave, the distance between any two consecutive crusts or troughs is lambda. But here the distance between any two nodes or antinodes is lambda by 2. Try to understand, lambda by 2. Okay, so now this is a key point to understand. Either the distance between antinode to antinode or a node to node will be how much, children? Lambda by 2. Okay, now fine. So now actually this is a situation for suppose, children, okay, now if it is plugged exactly at middle, means middle, if you can plug, a one loop is produced. Is it clear? Which means what? It's a frequency with a 1. So its a frequency is how much, children? Its a frequency is how much? F. Frequency is how much? Frequency. Now let us calculate the wavelength. So here, children, as L is equal to lambda by 2, so let us say it is a case A, case B, case C. Okay, na? So here for case A we are talking about is length is equal to lambda by 2. From this we can say lambda is equal to 2L. Let us say lambda A in the first case. Okay, now fine. In the second case, if it is plugged exactly 1/4 of its length, the two loops are formed. Hence, the frequency is 2F. And in this case, lambda, how the same length L is equal to lambda by 2 plus lambda by 2. Okay, na? So in a case B, children, in a case B, so length is equal to lambda by 2 plus lambda by 2. So this is going to be 2 lambda by 2. So this, let's say lambda B, this is, so lambda B is equal to 2L by 2. 2L by 2. Clear? Fine. Now if the same string is plugged at a 1/6 of its length, 3 loops are formed. 3 loops means how many nodes are formed? 1, 2, 3, 4 nodes are formed. Then this will be lambda by 2, lambda by 2, lambda, means the length is equal to lambda by 2 plus lambda by 2 plus lambda by 2. How much? 3 lambda by 2. So here the frequency is 3F. Okay, now the length L is equal to the 3 lambda by 2. Lambda C, let us say. Now here lambda C is equal to 2L by 3. So now examination point of view, they'll ask the, what we can say, frequency of the modes of vibration. It is the F, 2F, 3F. So we can say the 1:2:3. Is it clear? So frequency is 1:2:3, fine. But the wavelengths very important. So it is lambda A is to lambda B is to lambda C is equal to, so let us take that. So first lambda, it's a 2L is to 2L by 2 is to 2L by 3. Is it clear? Now, how much it is going to be? Look at it. So, it is going to be 1 is to 1 by 2 is to 1 by 3. Now, this is going to be 6 is to 3 is to 2. So, this is the ratio of the wavelengths of the modes of vibration. Frequency, my children, again I'm telling you, frequency you can relate here. So, FA is to FB is to FC is equal to 1 is to 2 is to 3. So, frequency is 1 is to 2 is to 3, but here wavelengths are 6 is to 3 is to 2. Is it clear? Fine. So, note down this examination point of view, very important. So, based on this also we can expect the numericals. Based on this we can expect the numericals. Is it clear, children? Fine. Okay. Now, children, let us see the damped vibrations. So, now till now we discussed about the natural vibration, which means what? Vibrations are happening in the absence of external force. I mean what? In the vacuum only. But what if medium is present? So, the vibrations so produced we can call the damped vibrations. So, which means what here? The periodic vibrations in the presence of external medium. I mean, so external resistive force acting on it or called what, children, here? Damped vibrations. So, examples what actually? The oscillations of pendulum in air, vibrations of a pendulum, vibrations of a tuning fork in air. So, even just you can hold a branch of the tree, just pluck it and leave it. So, it will be vibrating. Yes, it is also example for what, children? Damped vibrations only. So, means what? The vibrations of any objects in the presence of some medium or in presence of external resistive force are called damped vibrations. And the children, so the body executing damped vibration, children, it experiences two kinds of forces. It's very, very important. Two kinds of forces. So, the first one is what actually? What we can say, restoring force. Restoring force. What is that? Restoring force. And whereas the second force is resistive force. Resistive force. By the medium I can say resistive force. So, what this restoring force will do? The moment when you can just take, for example, take a simple pendulum. When you try to take a side and leave it. So, it will try to go here and it will try to come back to its mean position only, right? Means there is the force which is trying to bring the object to its original position is what actually? Restoring force. What is the resistive force? Yes, medium is present. The oscillation should happen or the vibration should happen in the presence of medium. Then what will happen? That particular medium will try to resist. So, exert some force in opposite to the direction of the motion of the simple pendulum. If you can take the simple pendulum as an example, that's what will happen after some time. Simple pendulum will come to the rest. Initially, it might be oscillating like this, oscillating, but as time passes, slowly its amplitude decreases. After some time, what will happen, children? Yes, oscillations are ceased. In examination part of this very, very important question, why the oscillations ceased after some time here, children? So, here as I told you that here there is a resistive force. To overcome the resistive force, the vibrating body has to spend some energy. So, for every one oscillation, it is spending some energy, which means what? Rather we can say it is losing energy. For every oscillation, to overcome the resistive force, it has to spend some energy. So, here energy is lost. Energy is lost. As energy is lost, slowly, completely after some time, energy will become zero, where it won't be in a position to oscillate. Is it clear, children? This is very, very important. Yes. Now, here again I am telling you, the amplitude, very, very, very important. Amplitude is not a constant, children, here. Amplitude decreases as time increases. Now, examination point of a displacement time graph. There you can see, I'll try to show on board also. There you can see, children. So, this is a displacement time graph of a, what we can say, damped vibration. Here you can notice, so as time passes, in beginning you can see, children, there, so amplitude is a maximum, but as time passes, what is happening here? The amplitude is slowly decreasing. So, after some time, it has become a zero. Clear? So, examples, as I told you, oscillations of any objects in presence of a medium. Okay, all comes under damped vibrations. Clear? Fine, children. So, this is about damped vibrations. Now come to the forced vibration. Come to the forced vibration. So what is this forced vibration, children? Here, what is the difference between damped vibration and forced vibration? In a damped vibrations, once we'll apply the force and we'll leave it. But whereas forced vibration, continuously we'll be applying the force. If a body is not in a position to vibrate, but still we are forcing. We are forcing continuously. For example, look at here. Here the body is there. So here I am continuously tapping, right? So what will happen? As a result, some sound is produced here. Actually, if I stop my external force, if I take out my external force, it will stop. But what will happen? I am continuously applying the force. So then as I am applying the continuously, periodic this. So the periodic vibrations produced under the influence of external periodic force acting on it are called forced vibration. I repeat once again, children, here. So the periodic vibrations are vibrations produced under the influence of periodic external. Periodic means what? Repeatedly it is acting, repeatedly. Periodic what? External force acting on it are called forced vibration. Children, here the body executing damped vibrations can experience two forces only. But here the body executing external, what we can say, external forced vibration can experience is exerted by three forces. What is that? First one, children, unless I raised up. Okay, well, so first one is what actually? A restoring force. So let us say restoring force Fr. Okay, now second one, what we can say, a resistive force. I can write like this, resistive force, like a so-called frictional force. And third one, children, very, very important. This is external force. External force. So there are three forces will be acting on a body which is executing forced vibration. Example, children, is continuously, what will happen? The string of the instruments which are having the strings. So continuously, what will happen? Will be applying the force. They will be executing, so that sound is produced. Drum will be there. There will be beating. So continuously as we are beating, what will happen? That membrane will be getting vibrated. As a result, some sound is produced. So many examples are there, but difference, what is the difference between damped vibrations and forced vibrations? In damped vibrations, once we will apply the external force and we remove. But under here in the forced vibration, continuously, that's called periodic external force, means continuously the force acting repeatedly. Okay, now fine, children. Yes, so here one important thing, children, for suppose, so let us take just example. Let us take here is a tuning fork. Let us say the vibrating body. Tuning fork I am taking as a vibrating body. Okay, now, and here just, children, to just give a clarity about the concept. Now, this example, this is not exactly matches. So just let us take. So it is a hammer, so called external force. External force. So then what will happen, children? As we all know that every object has its own natural frequency. Now this tuning fork is hit with a hammer, rubber hammer, continuously. What will happen? It will be vibrating. It will be vibrating continuously. Means this tuning fork will be vibrating with its own natural frequency. Vibrating with its own natural frequency. Let us F naught. It is a natural frequency of a body executing what we can say forced vibrations. And here this external force also has some frequency. External force also has some frequency, right? Yes. Generally, what will happen? It's not compulsory that the frequency should match. But what if the frequency of the natural frequency of the vibrating body? Okay, now, the natural frequency of the body executing natural vibrations. Okay, it's not a natural vibration, sorry. So the natural frequency of a vibrating body matches with the frequency of the external force applied on it or acting on it. Then what happens? Children, this is going to be the very, very, very special case. Very, very, very important. Very, very, very special case. So what if the frequencies matches? Then here we'll get one special phenomena called resonance. So resonance is the special case of forced vibrations. In exam they'll ask a question. What is the conditions to occur a resonance, children? So in a resonance, the natural frequency of vibrating body must match with the frequency of the external force applied on it. Then as a result, what will happen? If frequencies matches, what will happen? For suppose, okay, let us say that the natural frequency of the vibrating body matches with the frequency of the external force applied. Then what will happen, children? Very, very, very important. Then, so here one louder sound is heard actually in a resonance. Very, very important. Louder sound is heard. But in exam they will ask a question. Why louder sound is heard, children? Because when they are executing, what we can say, when they are executing resonant vibrations, they will be vibrating with increasing amplitudes. Very, very important. Means what will happen? The amplitude of the vibrations increases, and we know that here, we know very well that loudness is proportional to the square of the amplitude. As amplitude increases, obviously loudness also increases. Loudness also increases. Hence, as a result, louder sound is heard. Clear? So, children, here the condition is very important. What is that condition, children? Here, the natural frequency of the vibrating body must match with the frequency of the external force acting on it. Is it clear? Fine. Now, children, applications, let us see, examination point of view, definitely we can expect the question based on the applications of resonance. Applications of what, children? Resonance. So, here, look at here, it is one of the important and examination point of view, again, it is a famous one. So, let us take a 4 simple pendulums. Let us simple pendulum A, simple pendulum B, here is simple pendulum C, and here simple pendulum D. Let us take like this. So, 4 simple pendulums with a different lengths are taken. So, it is very clear that, so here please try to understand. Then what will happen? For suppose, if this simple pendulum is disturbed or it is made to vibrate continuously, then slowly these vibrations are passed along the string. Then after some time, we will notice that A, B, C, D, these 4 also executing vibrations. Is it clear? Fine. But after some time, we will notice that. So, pendulum A and the pendulum C will be continuing their vibrations with increasing amplitudes, whereas the oscillations of B and D are ceased. What is the reason? So, first by seeing this only, yes, you can see that here length of A is equal to length of C. Hence, the frequency of pendulum A is equal to frequency of pendulum C. Very simple. Okay. Now, means what here? What is happening? As their lengths are same, this frequencies matches. Here pendulum A is forcing other pendulums to vibrate, right? But here what is happening? The frequency C matches with the frequency of A. Then both will be in resonance. In a resonance, what will happen? Both bodies will be vibrating with increasing amplitudes. So here A and C, very important examination point of view. A, C, both will execute resonant vibrations. Resonant vibration, very, very important. Then what about B and D, children? What are B and D? It is a forced vibration. Some students will get doubt. Sir, why not damped vibration? See, damped vibration means what? Only only external force should act. But here, as A is vibrating, so A is forcing B, C, D also vibrate, right? Of course, after some time they might stop. That's different case. But here continuously sending vibrations due to the impact of A, B and D also, for some time they will vibrate. So here A and C will execute resonant vibrations, B and D will execute what, children? Forced vibrations. Clear? Fine. And let us take one more example where generally whenever we are traveling in a vehicle, especially let us take in a bus. Okay, na? So bus, what I mean the bus. If it's an old bus, if it's old bus means, so we can feel the impact more actually. So when the vehicle is going, even in a cars also, same thing happens. When we are going in a vehicle, we can hear the sound. But at a particular speed, what will happen? A louder sound is heard in a vehicle. At that particular speed, what will happen, children? The frequency of the engine matches with the frequency of the vibrating bodies. As the vehicle is going, some parts will vibrate, right? Which means what? They have their own natural frequency. These frequencies matches. When the frequencies matches, they will be in resonance. In a resonance, louder sound is heard. Clear? Fine. And here one more thing, children. So whenever our great brave soldiers, they are crossing the suspension bridge, they are requested or they are instructed not to cross that suspension bridge or march fast. Why? You know the reason? The reason is that the bridge has its own natural frequency. And our soldiers also, they will be, how they are walking, children, goosebumps will come, right? Goosebump movement. When the soldiers are walking, what a style, what a marvelous movement, I can say that. Okay, see, all will be tuck, 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 tuck will be, means they'll try to apply the force at the same time, right? Which means what? They will force the, what we can say, suspension bridge. Due to that, suspension bridge may vibrate. So the suspension bridge might have some natural frequency. And these people, that our great brave soldiers are executing force, yes, it has some frequency. So then if the natural frequency of the suspension bridge matches with the frequency of the force applied by the soldiers, then what will happen? Bridge will be in resonance. So in resonance, what will happen? It will vibrate with a more amplitude. So due to which it may get collapsed. That's what our soldiers are asked not to march fast. Clear? Fine. And even children, in a TVs or radios, if you can see a radio, in the olden days we used to have this kind of radio. So here tuner will be there, okay na? So here that antenna will be there. So generally, in order to listen the nice music and a clear voice, we will be trying to adjust the tuner. But during that process, what is happening, instead oscillators will be there, they will be producing electromagnetic waves. Yes or no? So they have certain frequency. Let us simply frequency of the oscillator, let us say that. That frequency, you are trying to what we can say, rotate the tuner, which means what? You are trying to adjust the frequency of the oscillator with the frequency of the radio waves. The moment when the frequencies matches, it will be in resonance. In a resonance, a louder and clear sound is heard. That is the reason why we are trying to adjust the tuner. Is it clear, children? Fine. So these are some applications of resonance. Is it clear? Fine, children. Just copy it. This one, density of the medium. Fine, children. Now we will see the characteristics of the sound actually. Children, mainly we have three characteristics. First one is loudness, second one is pitch, third one is quality or timbre. So the first we will try to discuss the first characteristic of the sound produced. What is that? Loudness. But before going to understand the loudness, let us understand the intensity. Why? Because loudness depends on intensity. So in a textbook, first they discuss about the loudness, but my advice is that first learn the intensity, then go back to the loudness. Actually, intensity, what actually? Intensity, all about actually energy. More the energy, more the intensity. Less the energy, less intensity. For suppose children, here energy is going, it might be sound energy, any energy you can take actually. So energy is passing. If this energy is passing, let us imagine one surface area. So this and the amount of energy which is passing through this unit area, okay, unit normal to this area, unit area in a second, in a 1 second actually. So the amount of energy which is passing through the unit normal area in a second time is called intensity. In a given second, if more energy is passing, then more is the intensity, which will show so much of impact on our ear. Sometimes for sounds will be there, we can't bear actually. You can hear but you can't bear, which means what? More energy might have entered. So sound with a more intensity, we can say that. So here this energy passing through this unit normal area in a time, we can call it intensity. So the formula is what? Intensity is equal to energy by area into time. Okay, so energy is measured in terms of joule, children. Area is meter square, time is second. But joule per second, children, try to understand. Joule per second is nothing but watt. So we can say the watt per meter square. And here one important point, examination point of view. For ordinary sound, what is the intensity? The intensity of the ordinary sound is 10 power minus 6 watt per meter square. And one more important point is that here the minimum intensity of audible sound is 10 power minus 12 watt per meter square. Okay, now fine. And this intensity depends on 4 factors. It depends on amplitude, depends on the frequency of the sound, depends on the density of the medium, and even depends on the speed of the sound in air. So here intensity of the sound actually proportional to the square of the amplitude. It is also proportional to the square of the frequency of the sound produced, and is proportional to the density of the medium, is directly proportional to the velocity of the sound. So children, examination point of view, these 2 points and this unit Okay, and these factors are very important. Now come to the sound. So what is a, sorry, not sound, loudness. What is a loudness, children? So the characteristics of the sound which distinguishes what between a louder sound, distinguishes louder sound from a faint one is called loudness. Is it clear? Fine. Means if both sounds will have a same pitch and quality, then how can we distinguish that? Based on the loudness only. Okay, fine. Now let us take two waves here. So here one wave only. So frequency is same and wave pattern is same, hence quality is same. But they are different in amplitude. They are different in amplitude. Here amplitude is less, here amplitude is more. So this sound wave which has more loudness than this. Means more is amplitude, more is the loudness. Less is amplitude, less is the loudness. Clear? Fine, children. And here the unit of loudness is phon, P-H-O-N. And the level of sound is measured in terms of decibel. Some students are getting confused. So unit of loudness and the level of sound is measured in terms of decibel. Children, if this level of sound exceeds 120 decibel, it leads to noise pollution. It leads to noise pollution, with which what will happen if our body, our ears will get exposed to the sounds with more than this 120 decibels, and definitely we will get some health issues. It's not like the sound which makes us happy, no, rather it makes us to get irritated. Okay, now fine. And here, children, so this loudness depends on 4 factors. So loudness is proportional to the square of the amplitude, which means what? More is the amplitude, more the loudness. And loudness also inversely proportional to the distance between listener and source of sound. For example, children, very simple. If one of your friend is talking from near, so definitely we can hear clearly. If the distance between your friend and you increases, can you hear the sound with a more loudness? Obviously no. Means as the distance increases, loudness decreases. And third one, loudness proportional to the what we call surface area of the vibrating body. Surface area. The best example, the drums, let us take. One drum with a membrane will be there. If its surface area is less, and one more drum with a more surface area, in which case louder sound is heard, louder sound is produced. Obviously the drum with a more surface area. Okay, as surface area of the vibrating body increases, obviously loudness also increases. And the fourth one, last one, loudness is proportional to the density of the medium. Children, here based on this first relation, we can expect the numericals. It can be written as L1 by L2 is equal to A1 square by A2 square. Very, very, very important. Or A1 by A2 is equal to square root of L1 by L2. So sometimes the ratio of amplitudes will be given. They will ask you to calculate the ratio of the loudness, or sometimes what we can say, the ratio of the loudness will be given. They will ask us to find the ratio of the amplitude. So we can use these two formulas. Is it clear? Fine, children. And here loudness also depends on the presence of resonating bodies. If more number of the resonating bodies are present, obviously the loudness heard also increases. Okay, na? Just copy this. So this is all about the intensity and the loudness. Acha, here children, this just for sake of examination point of view, you can remember how loudness is related to the intensity of the sound. So not required how we got this expression, all these things, the derivation, not at all required. Just for sake of examination point of view, how loudness is related to the expression. If they'll ask you for MCQ question, sometimes it might be asked, then it is very, very useful. Clear? 3, 2, 1, go. Fine, children. So now we discuss about the pitch. Okay, so what is a pitch, children? So the characteristics of the sound with which we can distinguish, very, very important, acute note, okay, acute note from a grave one. Is it clear? And your pitch depends on the frequency. If more is the frequency, more is the pitch. Less is the frequency, less is the pitch. Okay, so look at here. So examination point of view. Okay. So what I mean to say is that here both will have same wave pattern. Obviously quality will be same. And the amplitude, look at here. Amplitude is 2 cm, here 2 cm only. Which means what? As amplitude is same, obviously loudness will be same. But what is here differ? What is the difference between these two waves? Number of waves. Here only one wave is produced. Here 1.5 wave is produced here. So here frequency is less, frequency is more. So pitch is less, pitch is more. Try to understand. So which means what here? pitch depends on the frequency. Pitch depends on the frequency. Here less number of waves, less is the frequency, less is the pitch. More number of waves, more is the frequency, more is the pitch. Clear children? Fine. And the last one is a quality. Last one, what is a quality? So what is a quality? Children, it's very very important. Two different musical instruments can produce a sound with the same loudness and pitch, but not with same quality. Why? Because the wave pattern of the sounds produced with the two different musical instruments will be different. They must be different. They must be different in a quality. Okay na? So here quality, children, quality depends on quality. It depends purely on waveform or wave pattern. This is time. Now children, look at here. So here two waves are formed, here also two waves are formed. So half wave, half wave, half wave, half wave. Hence what actually? Frequency is same, so pitch is same. And the amplitude also remains same. So as amplitude is same for these two waves, loudness is same. But can we say that these two waves are same? No, they are differ. What way they are differ? They are differ in wave pattern, waveform. Children, this is a wave pattern produced by the tuning fork. This is a wave pattern produced by the piano. Is it clear? So no two musical instruments can produce a sound with the same quality. They may produce with the they may produce sounds with the same loudness, same pitch, but not with the same quality. Children, there are three characteristics of the sound. First one is the loudness, depends on amplitude. Second is pitch, depends on frequency. Third one is the quality, depends on waveform or wave pattern. So children, so these are the topics, okay, of the sound. So children, again I'm telling you, as it is a one shot video, so in a shortcut, almost I think we try to cover almost all concepts. But my advice, my sincere advice to you all is that children, kindly refer the textbook. Of course, if you are near to the exams, so and it is also too difficult to cover the entire chapter with the textbook also, I can understand. That time it is very very useful. So children, again I'm telling you, already we had uploaded entire sound chapters unit wise. Links will be given in the description. Kindly go through that. And one more very important, children, so the moment when you start watching this one shot video, at least just be ready with a notebook, so that what will happen, you can note down the some important points, so that what will happen, you can remember. Children, don't get tensed, don't get confused, don't take a pressure, don't feel any frustration. Exams will be approaching, yes, quite natural. See, accept the truth, accept the challenge. Exams will approach, you have to face the exams, you have to get the best result. That's it, you have to. Can you run away from the exams? No, you cannot avoid the exams. So what writing the exams is mandatory. If you think in our life, children, if we are very sure that we have to face one thing, a situation or anything, children, so we should be ready, we should face that situation with so much of courage and so much of confidence. Don't worry, children, here we are with you. Any doubts are there, definitely just try to approach. You can mention your doubts in a comment box, or even just our channel number is given. Yes, you can see on our channel only, okay na? So yes, you can text your doubts through WhatsApp. Please don't give a normal message, and it's humble request, don't give calls also. Just try to give WhatsApp messages. Yes, maximum will try to respond and will try to clarify all your doubts, children. Okay na? Thank you so much. All the very best.